Okay, folks, welcome to, I think we're at week 4 of this quantum mechanics exploration. Before we start today, does anyone have any questions from last week about our lecture on unitarity and how we used a simple principle of unitarity to derive a pretty profound result? The fact that in quantum mechanics, position and momentum don't commute, that there's sort of this weird interplay between the two. And so I sort of took you through that whole long-winded derivation to sort of give you a sense of how unitarity works, how it's this sort of mathematical idea that is self-consistent, that allows us to go from one orthonormal basis to another, but also preserves all the tenets of probability, right? If you have u dagger u or u dagger, so on and so forth, everything adds up to 1, multiplies to 1. And so unitarity is this nice sort of mathematical device we can use and employ in our vector space. So today we are going to make a little shift. So far we've been talking about discrete quantities. Discrete quantities, what do I mean by that? Quantities that come in discrete integer numbers. So the spin of an electron, or I shouldn't even say electron, the spin of a particle, in the way we've been looking at it, is discrete. It comes in eigenvalues of plus or minus 1/2, or yeah, plus or minus 1/2, depending on the direction you're observing. And so these are discrete numbers that we can map up and point out. However, as you've seen in your first problem set, and as you should sort of be getting a feel for, as we sort of talked about the quantum mechanical algorithm, the quantum mechanical program, there's a little bit more weirdness that we have to fill in. If we think back to Stern and Gerlach, there were certain cases where we observed constructive and destructive interference, right? Where some measurements canceled out with other measurements, where some measurements added up with other measurements. And so there was a very famous experiment done called the photoelectric effect to prove the photoelectric effect. And it's actually the experiment Einstein won his Nobel Prize for, that showed experimentally that light was not only a wave, right? Light travels as electromagnetic waves, but also that it's made up of quanta, individual photons. And so there's this sort of duality between particles and their behavior as discrete bodies and discrete entities, and also their behavior as waves in this sort of wave-like manner. And so basically, when we go to this continuous framework, all of our description of quantum mechanics can now be described in terms of a wave function, which is a state vector, just like all of our discrete quantities, except it tells us something about continuous probabilities. So I know that sounds like a lot, but we're going to go through it slowly. So let's just think about this conceptually first before we dive into the mathematics. So what do I mean by wave function? It can be anything over all space, right? It can be periodic, it can be not periodic, and it's continuous, right? So we can call this psi of x, so it's called psi, we call it psi. And now, instead of my probabilities being quantized in discrete numbers, there's a continuous stream of probabilities. So let's say this is psi of x, and I'm measuring the position of my particle. Well, if I take 2 points, this would be the probability between x1 and x2. The probability of me finding my particle between 2 points would be this area under the curve, right? And so now if I took it between these 2 points, there's less of a probability of me finding it at this position. There's way more of a probability here, and so on and so forth. So the wave function is a state vector. The wave function is complex, right? Which is something that we have discussed as being a necessity in quantum mechanics, this sort of need for complex numbers, this need for complex entities. It's continuous over all space, right? And it tells us something about the probabilities throughout all space. Now you may be asking, okay, this is great. This is cool, this is nice, this is an interesting way to sort of describe the system. But how, this cannot be the wave function after I make a measurement, right? Because let's just say I make a measurement on a particle in this state, and I still have this as the wave function. I still have really no idea where my particle is, right? And that should intuitively be your thought, that if you make a measurement, somehow this wave function needs to change into a more definite state, right? It needs to be a more definite measurement, right? If you're in the lab and you're measuring the particle's position and you make the measurement, you're not going to see probabilities, right? You're going to see the particle in one spot. So mathematically, what are we going to do here? Okay, and there's something very nice and mathematical we can do to this wave function to collapse it. It's called the collapse of the wave function. So as Gabe has described to you, an object like this, we'll just call it phi, doesn't matter, is a probability amplitude. This is pre-measurement, right? This is not post-measurement. And in the beginning, in the first problem set, I used the word compounded measurement to describe this. When you take the norm squared. This is your state after the measurement, okay? This is the real probability. And so now I'm gonna show you why this is so intuitive. And here's why. If this is psi of x, if you take the norm squared of this, and by the way, the reason why this works mathematically is most of our psi of x's will be Gaussian. What do we mean by Gaussian? A Gaussian is just some bell curve kind of object, and it's usually an exponential form to some other prefactors. So now, if I take the norm squared, I'm going to get something like this. Okay, I just drew this very dramatic because you've never seen this. This is called a Dirac delta function. Okay. And the Dirac delta function is not a very well-defined function, but we're not mathematicians, so who cares? It's zero everywhere. And at the point where x equals, or x1 equals x2, the Dirac delta function goes to infinity. So now I have a definite, right, so delta goes to infinity. So now I have a definite measurement, okay, of position that is at x1 equals x2. Does that make sense? And obviously, you have to take the integral of this to figure it out precisely, right? And the integrals of these Dirac deltas are really, really, you can look at them and know what the integral is. That's why I gave you a few of them on the next problem set. So conceptually, this is where we're going. We're sort of, now we're going into this continuous space. And it's very, very mathematically intuitive. I mean, people always say quantum mechanics is really hard, and even general relativity gets a bad rep. And I'm writing a paper called General Relativity from First Principles, and in the abstract it says this is for high schoolers, right? Because the intuitive ideas are not very complicated. It's the physics that's more profound. So what the mathematical algorithm here is straightforward. Are we on the same page? Does anyone have questions conceptually about that before we, because when we get into the formalism, it gets a little dense. So I don't want you to sort of lose the intuitive sense of what we're doing here and what we're extracting and why we're approaching this problem in this way, right? Why is this even allowed physically, right? Why are we allowed to interpret nature in this way? Because to the physicist, the mathematics is only there to describe and explain what nature is doing, right? And so if nature dictates that this is not going to work, we have to change our approach. Okay, great. So then let's jump right in. Before I show you the real sort of mathematics that we're going to need, I just want to show you some quantum mechanical wave relationships. So do you guys know about de Broglie waves?
Yeah, they're the matter waves, right?
Matter waves, right. If you haven't heard of it, it's okay. It's a very simple idea, right? So a wave propagates at some frequency, right? And its energy can be determined as a function, as a function of its frequency, okay? So in de Broglie waves, you get this relationship that E equals h bar nu. Is that what you're familiar with? Or h nu? I don't know if you use the h bar, but actually you should use the h bar. So basically it's this relationship between energy and frequency. And this is true for matter waves, right? And so we can describe our wave function in a similar fashion, except we have to make it complex, okay? Because that's one of the requirements. Matter waves necessarily don't have to be complex, they can be completely real. So let's just describe a very general wave function. Okay, this is a very general plane wave. We call it a plane wave function. And I can write this as a function of position and time. That's a kx minus omega t, where omega equals 2 pi mu, right? And this is the frequency. And k equals 2 pi lambda to the minus 1. And this is what we call a wave number. And it's similar, it's kind of like a frequency. It's just a different parameter, which you'll see in your homework how this works more in depth. And from this, we can derive the following relationships quantum mechanically. E equals h bar omega, and P, the momentum, equals h bar k. Okay? And the important thing to note here is we have momentum, values of momentum now come in discrete quantities as multiples of h bar. Okay? So even though I have some continuous spectrum, I have a continuous spectrum in my wave function. The collapse of the wave function sort of augments that into a discrete kind of description or a discrete realization of the measurements. Right? So I have this continuous spectrum, I collapse it, and then I get a definite value of momentum. One thing I should note, there is a lot of debate. Actually, there isn't really any debate. There's a huge hole in fundamental physics regarding the measurement problem. It's sort of this idea that physicists just ignore and never talk about. And no researcher is really working on the measurement problem. And you know, it kind of is a big problem. It's one of the biggest problems in fundamental physics. This collapse of the wave function should be very, very, make you very uneasy. It just should, because it has a lot of strange implications, but it reproduces very accurate predictions and testable predictions, and so physicists just haven't cared. There's a number of philosophers that are looking into this, and philosophy of physics departments have sprung up all across the country in order to try and discuss the measurement problem. I took a class on it. I didn't really like it, but that's just because I was coming at it from the wrong angle, I guess. So I just thought I would just mention that, even though we won't really talk about that here, for those of you that are interested, there's a lot of stuff on this, including one really great Columbia professor named David Albert. I don't know if any of you have heard of him. He's sort of popular in that community, and just something to consider. Okay, does this all make sense? So now we've sort of gotten our quantum mechanical analogs to de Broglie waves, right? De Broglie waves being E equals h bar mu. Only difference is I now have these 2 pi's, which they're not as scandalous, I hope, as they once were. Okay. Okay, so let's start the quantum mechanical program from scratch, but this time with continuous degrees of freedom. Okay, so my first relationship is my projection operator, or my identity operator. That's not really clear. Can now be written as an integral of all space, dq prime, q prime, q prime. So this is my new projection operator. Right? We now know that the norm can be written like this, the norm squared, I should say. Psi star, we'll just say q prime, dq prime, psi q prime equals the integral over all space of psi q prime squared dq prime equals the integral over all space dp, right? So this is my full probability integral. So this is just, if you have questions, stop me. I just assume that this should be very familiar because we've done things like this with Rosenketz, sort of without these psi's. So the only difference now is we have integrals instead of summations, right? Summations are discrete operations and integrals are continuous operations. And so all of the same rules apply, probability, maintaining unity, and so on. Okay, I have one more condition. I want to say that my wave function vanishes at the endpoints. Okay, that's just a formal condition that we imply, that as the wave function goes to infinity, it must vanish. And this sort of implies that it's Gaussian in nature, right? Because only Gaussians can have this mathematical condition placed upon them. So, you know, I just thought I'd mention that. Right, and now we can even describe our normalization of states. So the inner product, we used to write the inner product as a direct, as a Kronecker delta. But now our inner product is going to become a Dirac delta, right? Dirac delta being that function that spikes to infinity. It's not even really, you know, every time I show the Dirac delta to anyone, any of my mathematician friends, they laugh and they say, what are you talking about? That's not a function. So for those of you mathematically inclined, I'm sorry. I'm not too worried though. Okay, and then we can sort of take this to the next step. If q minus q double prime does not equal 0, right? Right? Oh, sorry. If q minus q prime does not equal 0, then q prime does not equal q double prime. And therefore, my Dirac delta, q prime minus q double prime equals 0. And similarly, if q prime minus q prime double prime equals 0, and q prime equals q double prime, therefore, my Dirac delta is infinity. And please stop me if you have questions. I like questions. I like back and forth, or I'm just going to have to end up cold calling on people.
Wait, can you clarify, like, the 1 equals the integral of the projection operator? I thought the integral of the identity operator was 1, so, and the identity operator is like the sum of the projection operators, right? So.
Yeah, no, the identity, okay, let's make the language clear. I forgot that I didn't use that language before. Projection operator is identity operator. Same thing. Now, the fact that it's a sum over, it's fine. Now we've just made it continuous, right? And theoretically, I could have a ton of these projection operators in different bases. Does that make sense? Sort of lined up together. So it's implicit now. I mean, it's implicit. The fact that we have a complete set of eigenvectors is implicit. Is that clear?
Yeah.
Okay. I know that's not very formal, right? Because I'm sort of just acknowledging that you know that, right? That I can just create superpositions, right? I can create any combination of basis vectors and state vectors, okay?
I have a question.
Yes.
For the identity operator on the right, on the top, shouldn't it be psi star psi?
Yeah, there is a psi star.
Like psi star of q prime times psi q prime.
Yeah, there's the psi.
Oh, I'm sorry, I didn't see that.
No, that's okay. And I just ran out of space, so even though I got a nice big board, it's not enough. Okay, anything else? Okay, great. Okay, so let's think about what else we can do here. Okay, so if I have something like this, q prime minus q double prime dq double prime on this state, I get back my original, or I get back the same result, right? Because the points have to be equal anyway. That's all that's saying. Right, and so I get this relationship. Do I need deltas? Let me think. Oh yeah, I think I need deltas. Sorry. Right, and then I can even expand it to something like this. dp prime. Oh, no, this should be, yeah, an integral over p. A few quick things. Wait. Yeah, that's good. Okay. I have a few quick questions now. And the reason I'm going to start doing this is because in one of my lectures, the professor asked a lot of quick questions to make sure people were paying attention, and I really liked it. So I think I'm going to steal his technique. First thing I'll say, for those of you that aren't comfortable with integrals, you need to see me because it's extremely important, right? It's something we do all the time. And for those of you that want to end up doing research, it's very, very important that you are comfortable with them. And it's fine if you're not. We can go through them. Second thing I'll say is always pay attention to what you're, for those of you that are just starting, always pay attention to what you're integrating with respect to. Usually that's always what I do when I look at an integral. I just look at the measure, right? And I just make sure that that lines up. Now, can someone give me an interpretation of, first of all, these two statements make sense, right? I hope. This is very simple. It's just saying that q prime must equal q double prime, right? And so I can rewrite this in this way. Otherwise, this would just be 0 and this integral would just vanish. Okay? So does anyone, and it would vanish because it's improper, because of my bounds. If you had a term vanish in an integral, right? And you just had dq double prime and it was indefinite. Indefinite meaning no bounds. Then it would just be a constant, right? It would spit back the constant. But since we have bounds here, this actually does vanish. So now the question becomes, what is the interpretation of this? First of all, what is this telling me about the p states? And what is this telling me about the q states? Right? What is the function of both here? It's just no physics, it's just mathematical. What's the function here? Anyone want to kind of briefly mention? Just shout out.
I mean, there's the projection operator over p prime.
Good. So I have a projection operator with p prime, right? And I have a complete set of states q prime, right? So somehow I'm using the projection operator, right? In some way, I mean, it's not really doing anything physical here, right? It's not. It's just sort of spitting this back. But it's important to think about what the sort of makeup is, right? So that's all. That's all I wanted you to get at, is there's a projection operator here, and it's spitting back to me position, an inner product of positions, okay? No eigenstates, no eigenvalues here. Is everyone okay with that sort of terminology? And does everyone sort of understand that this is just a scalar? If you're not, speak up now. I'll say one thing. I'm totally okay if someone doesn't get something. I know it's kind of, in high school, people don't like to ask a lot of questions. Do that here. It's okay. We can go back and review it, but this is not a vector, okay? Very important. Okay, now we're gonna continue. We're going to describe some of the same quantities now. In a different space. So again, I have this relationship. Okay, a projection operator of momentum. I have this, which is now a Dirac delta. I can also rewrite this as any function of plane waves with my normalization. This would be I q prime p prime. And if I did it the other way, okay? So this is just the analog of my plane waves kind of argument. And now we've come to a crossroads now. Give me a second to write that down. We've come to a crossroads. When I drew the very bare schematic of position, if I asked you, okay, if all I gave you was that graph, and I asked you, give me the momentum, what would you say? Because that's the big question now. First of all, I just want to say this. In physics, everything can be determined by positions and velocities. That's all you need. Momentum being velocity. Mass is not so important. So what would you say to me if I just drew that random schematic that I drew from the beginning, and I asked you, give me a momentum eigenstate, or sorry, give me a momentum, give me a momentum eigenvalue, right? Take the norm squared of this wave function and give me a momentum eigenvalue. What would you say to me?
How?
How? Exactly. You'd be like, what? What? What a silly question. There is no momentum here. So we need some way to get between momentum space and position space, right? They're sort of two separate geometric things. Two separate geometric things, two separate bases, two separate realms. So we need a relationship between momentum and position states. Is that clear? So I'm trying to motivate this stuff, because usually in a quantum mechanics class, they throw up, oh, this is position, this is momentum, this is a... No, we want to sort of really understand why we're doing this mathematically. So now I'm going to show you that relationship. And to go from one one basis to another basis, I have to get the language right. We just do a Fourier transform. And for those of you that don't know what a Fourier transform is, it sounds very fancy. It's not. It's very, very simple. And for most of the rest of the lecture, other than playing around with uncertainty, we are going to explore momentum space and position space in this sort of abstract way, okay, using Fourier transforms. So let me give you the basic idea. Okay, so if I have a vector in position space, psi of q prime, I can rewrite this in this way. Okay, d p prime over 2 pi, okay, e to the I, p prime, sorry, this should be a q prime. I mean, it doesn't matter, but just for convention. Q prime, p prime, psi of q prime. Okay, similarly, if I want to go to momentum space from position space, I take the Fourier transform, which is just this. Okay, and I'm going to explain this in a second. I'll just let you get that down.
Wait, are you going to explain where you got the initial like 1 over square root of 2 pi e to the?
Yeah. Okay, so first of all, this is just a Fourier transform. It's nothing crazy. And you'll see how this works. It means this should be a p prime. Okay, and it's going to take us from momentum space to position space. Now, Kelly asked a very, very, I'm not saying this in a rude, annoying question. Everyone asked about 2 pi's, square roots of 2 pi's, normalization. Here's what I'll tell you. I'll tell you how I got these 1 over 2 pi. You know, Feynman had a very famous quote. You'll see this when we do QFT. So fine, I'll give you a story about normalization now, okay? Because every physics student must hear this. In Feynman diagrams, you have a lot of deltas and you have a lot of delta functions and d's and all that. And Feynman told a graph, and some of these factors give you 1 over 2 pi's. Some of them give you 2 pi's, normalization factors. And he told his graduate student, if you don't know your 1 over 2 pi's from your square root of 2 pi's, you don't know nothing. Okay, now I'll explain to you. Notice in our wave function Ansatz, guess, we had a factor of 2 pi, right, to maintain unity. The only reason I'm bringing up these 1 over square root of 2 pi's is because I already know that I want them to cancel out at the end. That's the only reason. So it comes from experience, I like to tell people. Because if you didn't have these normalizations, you would have so many factors of root 2 pi's, 1 over 2 pi's all over the place. And then you wouldn't know what to do with them. And they don't make sense physically. So that's the best explanation I can give you. They're not derived from anything other than that, other than the fact that you already know intuitively that these 2 pi's pop up in our sort of wave functions, right? Because e to the I 2 pi is what? E to the I 2 pi is what? It's just 1, right? So that's why these 2 pi's pop up. And that's why these pop up, because when you do the derivatives or the you're going to get factors of 2 pi's out. Okay, that's really the only reason. There's nothing profound about it. And you'll see this in field theory, where we have a bunch of dp3s over 2 pi cubes and 1 over 2 omega k's. And the amount of times you'll write this integration measure, you're going to get sick. You're going to be writing this like 40, 50 times in one calculation. So everyone just does this. We just rename it so we don't have to keep writing it. So that's all that is. Okay, do these expressions make sense? Anyone have questions? Okay, so let's play around with this. Let's see if this actually works, or is this just kind of just random? Have any of you been exposed to a Fourier transform in high school? No? Okay, that's fine. It's not very deep. Which I will say, as in most things in math, it's not very deep. You just need to know what's going on. You'll figure it out. Okay. Okay, so I came up with this wave function. Let's see if this works. Okay, what did I write here? I wrote, okay, psi of q prime equals 1 over pi to the 1/4 e to the minus 1/2. I think I put a minus there. What did I do? Yeah, q prime squared. Okay, so this is my psi. Let me make that more clear that it's in the exponential. Okay, so I have a wave function in position space. I need to get to momentum space, right? To talk about momentum eigenvalues and eigenstates. And so I just do the Fourier transform. So I would start computing, and I'm going to compute it too. Let's see if we get the same answer using the formula I just gave. So psi of p prime equals equals the integral from minus infinity to infinity of e to the minus I. Yeah, q prime p prime psi of q prime dq prime equals, oh, I forgot my normalization. Just put your normalization in front. I don't know why I did that. So now I'm going to sub inside. This I can pull out. And I'm left with this. Right, and now it's simply a matter of computing this integral. That's all. So let's do that. I do these in a very weird way. So if you have your own way of doing it, that's fine. I just want to make sure I'm doing this computation right. Yeah, okay, good, perfect. Okay. Wait a second. That's fine. Wait, I'm stuck. Oh no, this is good. It worked. Okay, good. Sorry, that was on the fly computing because I just made this up this morning, so it worked. It worked. I get back psi of p prime. Okay, so I did the Fourier transform. I wanted to move to momentum space. I did this gnarly integral, which, you know, yeah. Only reason I kind of know what to do is because I've seen these probably 1,000 times by now, and I just know what algebra I would want to do. You can do them your own way. You're going to think Wolfra Alpha does them, or SimLab, or whatever, and see how to do these. That would be a good idea. And then I get back psi of p prime. Notice it has the same form, right? Which is to be expected. It's not going to be radically different. Also, the reason it's not radically different is because this is kind of a boring wave function. There's nothing really going on here, right? There's sort of one dependence on q prime, right? If I had more terms with q prime, this might have looked radically different. Right? So it also depends on your psi. And we're going to do an example where the psi is totally different. And you're going to see how the Fourier transform adjusts it geometrically. Okay, let's do the second integral. Or do I want to leave that as an exercise? Yeah, I leave that as an exercise because we're going to do another example. What you should do as an exercise is you should take the Fourier transform of this. And what will you get back if you take the Fourier transform of this? Someone want to shout it out? What should you get back if you take the Fourier transform of psi of p prime? You better get back what you started with. Okay? If you don't get back what you started with, this isn't working right. You know what I mean? Right? Because we're going from one to another in the same sort of like a mirror. Right? That's how I like to think about it. You start with q primes, you want to go into momentum space, you carry out this procedure, you want to go backwards, you just do the Fourier transforms back and forth. And I think Wikipedia has a nice article of what Fourier transforms are doing geometrically, although we'll see that. Okay, so that's an exercise. I'm not going to go through it. It's basically the same steps. Notice, Kelly, no 2 pi's, no root 2 pi's. I took care of it. I took care of it. Right? Because think of this. 2 pi is just a multiplicative constant. It's useless to have that there. Right? If you multiply by 7 pi, it doesn't matter. The only reason we chose 2 pi is because of the way it works with E. That's it. Okay, and now I'll give you this following identity, which is crucial. Not crucial, but nice. Every quantum mechanics student should know this identity. Capital Phi, because I don't want to. Okay, that we have an equivalence between the probability amplitudes. Sorry, the probabilities, not the probability amplitudes. And that means that this is Percival's theorem. Probably not spelling his name right. Folks, does this mean that the continuous spectrum looks identical? No. Okay, so don't, psi and phi might be totally different spectrums. Does this mean that we have the same eigenvalues? No, exactly. This doesn't mean we have the same eigenvalues. Very good. It just means that they both go to infinity. That's all. That the collapses are the same. It means nothing about the eigenvalues. It has nothing to do with their spectrums. Otherwise, uncertainty would make no sense. So don't, always question the mathematics. Don't just think because I write something on the board, it's correct. It might not be. I'm not perfect, and I'm not a genius, so there might be some errors. So very important. So good intuition. Okay, now we're going to do a much more complicated example. And I'm going to map it out geometrically. And we're going to take Fourier transforms. Is everything clear so far? It's very systematic. We're building one thing off the other thing. Okay, so I'm going to spell out the problem. We'll take a 5-minute break. We'll compute really, really fast. And then we'll do uncertainty. And I sent out a few pages about uncertainty and variance, so we don't have to go through all that probability. It's boring. So we notice something very, very odd. right, we notice that this quantity is really weird. We've lost our normalization to 1 for this inner product, right? Now, that should be quite intriguing, right? This is like, what is the interpretation of this? Well, it tells us one really important thing. We cannot definitely measure position to a T, right? What this is telling us is that position is really some spectrum of values. And that when we square this, we get some definite value, but it's not 100% definite. It's like 98% definite, right? That's all this is saying, which is okay, because for practical purposes, it doesn't matter. But you know, this should be a little, this should give you pause that we lost our normalization, because usually our inner product here in discrete space would just be 1, right? And so what is this? So I just wanted to give you. So now let's talk about how this continuous spectrum manifests itself in position and momentum space. Okay, let's do it. Let me see what crazy thing I can. Okay, I'll give you a quick note. Please do not be held back by my notation here. My notation here is very confusing. I'll say it right away. Just pay attention to the integrals that we're doing and pay attention to the results. Don't give too much thought to all my notation. I just did it in my own way because in the textbook, it needs to be structured like that. But for this purpose, just don't pay too much attention to my notation. Just pay attention to what's going on and the physical meaning, and pay attention to how we're doing the integral. That's important. So let's set this up. Yeah, so let's set up this kind of state. What were the bounds that I put? Q prime. Yeah. Like I said, don't pay. I'm going to draw this out for you anyway. So. Just have to write down what I wrote, and then after that, it's easy to compute. Okay. This is the sort of wave function I've set up. I'm integrating over some range between Q prime and delta Q prime. Okay? And I want to extract some position probability, right, between 2 points. That's all this is saying. If the notation is confusing, just don't worry. Don't worry too much. And I want to call this thing psi of Q prime. If you see what I'm doing, that's good. But if you don't worry too much. Okay, so it's some wave function. There's a lot of Q primes and Q double primes. It's just, I just want to show it to you in this way just because it's my notation. And all you need to know is I'm integrating over some range between Q prime and some delta Q prime to extract some eigenvalue. That's it. Or to extract some position state. Or not position state, position eigenvalue. Right, and then we have the following relationship. Which that doesn't even matter what your wave function is. This is implicit. Okay, just put that down there because we're going to make sure that holds. Okay, and we're going to integrate something like this, and we're going to see graphically what this looks like. Then we're going to go to Fourier space, momentum space, And we're going to see what that looks like graphically. And we're going to see if the spreads are different, right? Are the spreads, are the spectrums different? And then we're going to do uncertainty, rapid fire uncertainty, just because you see the principle. We don't use it a lot in practice. So, okay, let's take a 5-minute break till 10:25. And then we'll come back and crank this thing out. Quick updates during the break. Tomorrow is my normal question day. If you have questions, if you want to talk about your research, tomorrow's the day to do it. Isha, how are you doing?
I'm doing well.
You're doing well?
Yeah, I had some technical difficulties this morning, so
That's okay.
yeah. How about you?
I'm doing good. I unleashed my inner confusing notation, so it was going to happen at one point. So, are you moving? Oh no, I don't know if your screen's frozen. I can't really tell.
Oh no, that's like my picture that I had for my Stony Brook account.
Oh, okay, okay. So,
Yeah.
so it is a screenshot. Okay. Oh man. Let me just make sure I did this right. And then you're gonna have 2 points. Yeah. I got this nifty eraser, Isha. I don't know if you noticed. This thing is a beast. It's like so great. My eraser from last time was throwing dust everywhere. So no.
Where did you find it?
Amazon. You know, this board was such a pain to hang up. Only reason I got it is because I'm not going to be on campus for God knows how long, and I would probably not survive without a chalkboard. It's not possible. So.
What happened to your old chalkboard?
The tiny one?
Yeah.
Yeah, it's too tiny. If you want it, you can have it.
No, I have like 3 whiteboards in my room. So.
Whiteboards? Oh my God, Isha. It's over. It's over. I can't be your friend anymore.
What's so wrong about whiteboards? They're fun.
No, they're fun. They're fun.
They don't leave any they don't leave any dust.
That's true. That's true. I think it's more like superstition and like what, like I don't know. It's just weird. It's like I can't come up with things at a whiteboard. I don't know. It's more of a me problem. And some people's thumbnails are so nice. We have a dog. We have Isha's Stony Brook ID. Wonderful.
I don't know why, like for some, it changes. So like it flips back and forth between like the actual picture and the name of the person. Yeah, I'm not sure why it does that. But...
Okay, let's get going. Any questions? Okay. Okay, so for time's sake, I'm going to plot what this looks like, and then we're going to do the position integral. That one's more challenging anyway, but let's just plow through. So let's draw what this looks like graphically. Okay, so obviously I'm going to get some spread. And I get my psi of q prime delta q double prime of q double prime on this axis. And you'll find that if you do this geometrically, you get something like this. Okay. Okay, and this is what the spectrum looks like. So this is sort of visual for those of you that have trouble visualizing the mathematics. It's a spread, but I would argue it's pretty definite. Like this isn't the worst spread. Like the uncertainty here is not too big. Would we agree with that? I mean, if I had something way more spread out, I would be a little bit, more concerned about the definiteness of my position or the definiteness of my position space. This is sort of kind of nice. It's zero everywhere and it's kind of definite in this sort of area. Okay. So I'm not gonna do that integral because it's good for your practice and this is actually more important than doing the computation. We're gonna do the p prime integral now though, because I wanna show you how to do these kinds of integrals. So let's take the Fourier transform. Any questions about this? So, we're getting a real spread. That's the point. Okay? So now let's take the Fourier transform, which is a very messy integral. So just bear with me. We'll get through it. By the way, I'm very sorry. On the next problem set, there are some very messy integrals. But here's the way. You need to do some of them. You need to do them because it's just a rite of passage, right? It's like if you play cello. If you can play the Bach suites, you have just plug it into Wolfra Alpha. I'll know if you did that. I'll know if you did that because it's obvious when someone plugs in. You can do that to check your work. And Johnson, in practice, when I'm computing integrals, never mind, I won't say. Okay, I'm kidding. I don't use Wolfram Alpha. I don't even have Wolfram Alpha on my computer. Okay, I promise. Okay. Okay, let's just do the Fourier transform. And this integral is so messy, I did it out on paper this time. So we don't have to get all my mistakes. So let's do it. So I had some psi of q prime, delta q prime, p prime. And I want now I want it in momentum space, right? I had psi of q prime, delta q prime, q double prime. And the notation here is just, this is telling me my bounds, or the 2 points I'm integrating in between, right? This is integrated over all space, and then it's just a Fourier transform in position space. Q double prime, Q prime, delta Q prime of Q double prime, right? So this is just the expression for the Fourier transform. And then let's do this integral. Let's see what we get. I just did it on paper just so I don't have to stare at this for like 10 minutes. Okay, then I got this. Yeah, this is not, it's actually not that bad, guys. It's not terrible. Okay, I'm just going to use some trig identities for E, sines and cosines. And I get an expression of my wave function in position space. I'm going to write this here. Yeah, good. Where I use the, did I use something weird here? Yeah, I use this identity. Oh, the bounds need to be, did I even do this right here? Sorry? Did someone ask something? The audio cut out. No? Okay. I thought I heard someone. Where I use this identity, which my bounds should be changed somewhere, I think. Oh, yeah. Sorry. Sorry. Yeah, never mind. That's when we squared it. Okay. Okay, so I get an expression for psi of p prime just by doing this integral. And I get this graphically, which I did on, I just graphed it, and I wanted to see the spectrum. And it looked very different. So that's what you get. So this is kind of interesting. Does someone want to give us sort of an interpretation of this geometrically as opposed to the position spectrum? Not Kelly, someone else. How about Olha? What do you think? What do you think? How, if you were to describe your spectrum for position versus the spectrum for momentum, are there any comments on it? Just by taking the Fourier transform from one space to another space.
Like it's more undefined. I don't know.
Yeah, that's one way to put it, undefined. So what do you mean by more ill-defined?
Like,
what's a better way? Well, how would you explain that more?
so we can get a lot more different values, and
yeah, no, that's fine. That's fair. This spectrum is a lot more spread out, right? So that is definite at all. It's way more spread out. The spectrum could take a variety. Of course, the probability here is lower, but that doesn't matter, right? The probability here is a lot higher than the probability here, but it's more spread out than our position spectrum. So now we're starting to see something very, very interesting. We had somewhat of a definite spectrum for position, and we've compromised momentum kind of badly, right? And we just see that by just taking the Fourier transform, which is pretty remarkable, honestly. That's pretty cool. Okay, great. Now let's just verify that this wave function holds for probability, okay? And I just computed it here, just so you can show that, just so I can show you that those relationships are not just for paper. We actually want to confirm that our quantum mechanical conditions are held. So let's just do that really quick. So I have this integral, except now I'm going to square my wave function. And I want to make sure that when I integrate this norm squared, I get a 1. Okay? So what do I get? I did this in a weird way, but it's fine. If I just take this integral, delta q prime, p prime, prime, delta q prime, Q prime equal to Q prime squared. And I use this identity. And it all checks out that the norm squared, when I integrate, equals 1. Just a quick check for you. You know, just to make sure everything's working out and we don't get weird probabilities. Nothing too profound. Okay, now the million-dollar question. How does one quantify this uncertainty relationship? And to do that, we're going to need this idea of variance, right? So how many of you were able to take a look at the reading? I think there's a raise hand function on Zoom, right? Okay, I can see your hands. Never mind. That's fine. That's fine. That's good. That's better. Keep things less digital. There was a great piece in the New Yorker called "How to Get Rid of Screen Addiction," and they advocated for hiring a big lumberjack with a hammer who always stands by you if you use a screen. So I think I'm going to do that. I think that's good. So the more organic we keep this, the better. I kind of miss that. Okay. So then I can jump right into deriving uncertainty, the uncertainty principle. Then it's a very quick 2-minute calculation. So let's do it. Again, the uncertainty principle is it's kind of a principle, right? Like you don't ever use it to make computations, right? It's more of a statement that one must understand about quantum mechanics, right? It's sort of, the commutator is different because the commutator, you're actually using it to compute, right? So here's an interesting question I have for you. Well, I'll ask you this after. Let's just derive the uncertainty principle. And there's sort of 2 ways to look at it. There's, I'll explain it at the end. Let's derive it. Using this simple idea of variance, okay? So I'm just gonna write this quantity. So now I have some delta Q squared, right? And according to variance, this is just Q minus this thing squared, I think. Yeah, right? Similarly, I can do the same for P. Right? This is just so, this is why I gave you this reading. So I don't have to go through all the probability. So I have this relationship. Wait a second. Yeah. Right. And now I'm just going to use this identity to sort of put this into a better form. Okay. So I have some delta Q, delta P, right? Yeah, and that works. Let me just make sure. Yeah. And what's the identity I pulled out? And you should obviously verify this identity. What did I do? 1/2 I over 2, 1 over I. Okay. Also, there are many ways to derive this. So if you look it up and you find a way that you like better, you know, use it. My way is kind of contrived with this identity. No, that can't be right. I hope I wrote this identity out right. I over 2. Yeah, no, I did. This should be the anti-commutator. I just made this up, so obviously verify it. Okay. So I can rewrite this expression as this. So this commutator. And then it's just really straightforward. I get the uncertainty condition, and I'll explain what the uncertainty condition is even saying. This is the uncertainty principle in Hermann Weyl's form. I can't really get the German on it. And he did this in 1928. So I think he might have derived it this way, except I think he did something weird at this step. So look it up. And then in Heisenberg's form, these just rigorously, there is a reason why these deltas are different. And he puts in the H bar. We just set H bar equal to 1, obviously here, and C equal to 1. And this is Heisenberg's form. And curiously, he came up with this in 1927. Okay? What is this saying? Why is this the limit? What does this even mean? Okay. I'll give you a second to copy. I encourage you to carefully go through the steps on your own if you want to, because I might have made some probability errors, but I think it's okay. Okay, so what is this saying? First of all, this is telling me something very interesting between change in P, change in Q. Okay, it's telling me that the more I know about Q, the less I know about P. That's the first very, very important thing. Let's look at this side first, this H bar over 2 or 1/2. All this is saying is there's a limit. This is the limit to how far we can measure accurately. That's all this is, right? So H bar is a very special quantity. Well, H is a very special quantity. Does anyone know where H came from? Okay, it's a very interesting story. So Planck used H to explain this problem called the black body radiation problem. I don't know if any of you have heard of it. Okay, great. It's a super interesting problem. And basically physicists for a while could, and that's kind of actually the birth of quantum mechanics, really, was to explain the black body problem, I would say. That's really why people looked at H and looked at quantizing, and that's really historically what happened. And I'm not going to explain the details, it will take a while. We will actually use black body radiation to motivate quantum field theory, actually. But you should look up black body radiation, and you should read why this H and H bar is like the lowest length scale we can measure at, right? Like the Planck length is the smallest scale we can get to, we can access, right? In other words, it's the smallest scale we can intuitively observe. Well, not really experimentally, that small, but it's really the limit of our observational power. Quick aside, string theorists need you to get 100 orders of magnitude smaller than the Planck length to confirm anything. That's why no one takes it seriously anymore, because that's like silly. Anyway, sorry. I shouldn't bash on string theory, but I do anyway. Okay. Great. Okay. And so this should be really weird. I mean, this is super strange, right? That it's like in a classical system, you have no loss of information, right? Like, there's no such thing as losing information about, like, if I told you the ball was at position X, but then I said, okay, you know nothing about its speed, that would be strange, because you could just use the kinematic equations and you could tell me what speed it is at that height given some initial conditions. You can't do that in quantum mechanics. Another very interesting thing to think about, and maybe this is something one of you want to do for your research papers, which, by the way, if you have topics, you should come tomorrow and we should discuss along with your other questions, or if you want to talk about being a physics student and so on. We've had some nice Sunday conversations, those of you that have came, is how this affects causality, right? That's something you should think about. Like, I'll explain. And then we'll be done for today. This is my last digression. This is just sort of extra, just to sort of, and then I have 10 minutes. Okay, so let's say you have this kind of diagram. And you'll learn this more if you take field theory. You have, you have position on the X, you have time on the Y, right? Backwards in time, forwards in time, whatever. And I want to say that light travels on 45-degree lines in this graph, okay? So this represents light. Now I'll explain what I mean. And it makes these cones at 45 degrees. Okay, now I've made a natural barrier. Let's say I have an event here, some position in time, right? And we'll call this alpha. Let's say I have another event here, beta. Don't worry too much about the diagram. You'll learn it. But the main physical idea you should know is if alpha is some event, let's say some of you folks are baking cupcakes, okay? And beta is some other event. Some folks are baking cake. If these two events are located on opposite side of the light cone, it means they cannot affect each other causally. There's no causal relationship. They're independent events. Okay. This means that the commutator between these two things, I know this sounds silly with cupcakes and cake, but it will be much clearer, is 0. It vanishes, right? You can know each independently. You can know all the information about each independently. Now, if the commutator doesn't vanish, that should be very, very interesting with respect to causality. And I'm not going to go into it too much in case one of you wants to write about this. Causality is in jeopardy here in a very interesting way. Just something to think about. And we know what a commutator is. We know the physical meaning of a commutator. We know why they're so important. This sort of is pushing you in a more abstract direction. Okay, just something interesting. And in field theory, when we compute the commutation relations in field theory for quantum fields, you'll see the same sort of ideas pop up. In fact, you'll see that the commutator between two fields in QFT, two fields phi and pi, which I'll obviously explain what those are, is also I, just with a delta function. Okay, so we're going to have another weird kind of thing popping up in QFT. It does not go away. That's what I want to explain, that this weirdness does not go away. Okay? Okay, let me outline some logistics for the last few minutes, and then Gabe will take over. So where are we going? Where are we headed? What's the trajectory? So let's just put this down. Rename this, because we don't do this often, because usually we have too much material, but I have some time today. For those of you that want to read ahead, next class, I don't know what date the next class would be. Whatever, next Saturday, we're doing angular momentum. Okay, so these are things like generators, Lie algebra of angular momentum. You're going to play around with the group of angular momentum, SO3, 1, that kind of stuff. We're going to do spin decomposition. We're going to do a lot of fun stuff with angular momentum. After that, we're going to go to basically quantum dynamics, where we didn't do the Schrodinger equation today. Today was just to get a sense of wave mechanics. Okay, so why am I writing mechanics? Dynamics. Right, so this is the Schrodinger equation, right? This is free particle solution, like very simple solutions of the Schrodinger equation, deriving it. We are not going to use the Heisenberg equation of motion at all. That was just for you to do in the homework, for you to see, for you to solve a problem with it, just so you know how to do it. Because the Heisenberg picture, as you know from your homework, the operators evolve with time, right? Not the states, the operators evolve with time, right? You had something like e to the I ht, b e to the minus I ht. The minuses could be flip-flopped, right? And this was your Heisenberg time evolution. This will be crucial in the path integral. And when we do the path integral for QFT, we use a lot of these. So that's why I wanted you to see it, but I'm not going to spend too much time on the Heisenberg picture. Okay, then we're going to go to specific systems. We are going to go to, and we'll do things like the infinite square well, those of you that want to do some reading, that kind of stuff. Then we're going to go to, I think we're going to do the harmonic oscillator. This is super important. For those of you that have taken any kind of physics, you know what a harmonic oscillator is. Quantum field theory is just an infinite number of harmonic oscillators. Okay, so you're going to see how that works. Okay. So this is like, I mean, if you learn nothing in this class, you need to learn this. You need to learn that. This is too important. Brian Greene used to have a very funny line, and he still tells it to us. He says, so everything you do as a physicist is just harmonic oscillators with corrections. And to some sense, he's right. To some degree, he's absolutely right. It's just harmonic oscillators with corrections. Okay, and then we'll do the hydrogen atom, which is sort of another rite of passage. We'll learn about spherical harmonics, Legendre polynomials. We'll do WKB approximation. And we'll do, we'll finish off with the path integral. I think we will be able to do the path integral, which Townsend covers a lot. Townsend has beautiful exposition on the path integral. And we'll add some things along the way. This is the basic outline. And then we'll take a month off. Then we'll do the heavy lifting, the heavy hitting. Okay, I'm also going to be holding some sessions during that break time as prerequisites for quantum field theory. Now, you don't have to come to any of them. I'm not expecting a lot of you to come just because, you might want to break. But I'm doing them because we need a lot more machinery to do QFT. Right? Quantum mechanics is not enough. But what I will say is I will be following textbooks for those. Like, I'm not going to be making up my own lectures. Quantum field theory, I will be making up my own lecture notes. So I'm not using a book. But for those few prereqs, I'll be following textbooks. So if you can't make it, I will literally send you the exact things I'm lecturing on so you can read them. I just think it's nice to hear it from someone, and then I'll also work out some other stuff and we can discuss, right? That's important. And I'm not going to record them. So it's kind of come or not. I just don't want to have that infiltrating. So what am I going to cover? And I don't have dates. I just want to give you sort of a lowdown on that. And then you can decide. We can figure out dates later. So we need to do special relativity. Obviously, very important because QFT is special relativity and quantum mechanics. That's what it is. So I think I'll do maybe 2 classes on special relativity during that break, hour long, not hour and a half. Then we need to do Lagrangian mechanics. Okay, Lagrangian mechanics is super important. So I'm going to do 1 talk on Lagrangian mechanics and deriving it and actions. And then we need to do, oh shoot, I forgot one really important topic in my list, scattering. We need to do scattering, okay? So very important. We'll add that in somewhere. And then I'll do 1 on, I think that's it. And maybe 1 on complex analysis, and that's it. So, we'll do 3 or 4, just to give you an idea of the break. Can someone remind me when I put the first research paper to be due in the syllabus as well? Someone have that handy? Because I want to just say something about that, important.
It's October 3rd.
October 3rd. And can you tell me the Saturday before that? September 28th, 27th?
26th.
26th is the Saturday?
Oh, wait. Yeah, it is.
Okay, yeah. I can't remember if that's 30. So 9:26, I want your topics. Okay, by 9:26. You can give them to me anytime in advance in case you want to start on it early and discuss it. For the research papers, is there a page limit or word limit? No. Could be 40 pages, could be 2. It's up to you. You have total freedom. Like I said, I don't really care. I want you to do the problem sets. That matters to me quite a bit. But if you want to do research with me, I would say these are mandatory. I don't feel, you should do these papers, okay? And another thing I'm planning, which I thought I would bring up, it's a little early for this, but we might be doing a session with, so I've done some work with this professor. Gabe knows her, obviously. Jan 11, you can look her up. I don't know if you've heard of her. But when she found out a lot of you guys were in this, and there's a lack of women in STEM. And when I told her we have a lot here, she was very interested to talk to you guys and sort of tell you what it's like being a physicist and that kind of thing. So I'm trying, we have to figure out a time. So that's on the docket too. So, you should look her up, get to know what she's done. She's great. I did a project with her a while ago and she was my professor for GR. So she's awesome. So yeah, topics by the 26th. You should get them to me early, right? Because I don't want overlaps. And I said this, I think, last Sunday morning. If you're not discussing this with me or your peers, you're probably not going to do a very good job. Last thing I will say, I want you guys to collaborate with each other now that we have a small size, right? I feel like we have a consistent group now. What do you guys think would be the best way to facilitate collaboration on the problem sets, on the topics, and even you might want to bounce ideas with each other about the paper, even though you need your own, you might want to work it out with someone else. So what do you guys think is the best way to do that? What platform should we use for that? Anyone have any opinions on it?
You could just make a group chat, I guess, like maybe on like, just to be able to talk to each other in one group. So I was thinking like maybe Facebook Messenger. I mean, that's a little bit specific, but whatever works.
Okay, yeah, no, that's fine. I won't be in it. This is for you guys. I just want to facilitate it. So I'll send out an email today and, you guys figure it out. Actually, that's difficult, right? Because we have a small group, but in my email chain, we have way too many people. So I guess what we should do is, I don't know how we should do this. Though all of you guys that came today, send me an email. I was there today. And then I'll make a group with you guys, right? and then you guys can make your own chat, right? Because you don't need a group chat with 150 people. And then I have over like 100 seniors who are like auditing and checking in with me. Like we don't want all those people. So just send me an email today saying, I was here today. I want to be in the group chat, because it's important you guys get to know each other and collaborate. A lot of you are high school seniors, right? All going to college. Who knows? Maybe you'll end up in the same region when you go to college. So it's good to make some connections now. It's good, right? And talk about physics. I like to tell people that, first of all, I love physics. That means by default, I love talking about it. And nothing is nicer than hearing young people talk. I'm young, but you guys are younger, so you're young people to me. Nothing is nicer than hearing students talk about physics. And the best thing ever is to hear two students argue about a problem. That's the best thing. So you need to do that. You need to get a feel for that. So let's make that happen. Okay? All right, great. Thanks, guys. I'll turn it over to Gabe. I'll make him host, and you guys will have a good problem-solving session.